Hi, welcome to a podcast on Solubility Product. Today we're going to learn in this podcast just about the basics of problem solving. I'm not going to discuss non-ionic equations or how solubility charts work or solubility rules or even how the process of something dissolving actually works. We're just going to talk about how to solve Ksp problems. So what is Ksp? It relates to ionic salts that do not dissolve well. If you look closely, this is a K, like we've learned about in equilibrium, which implies there's a ratio of products to reactants. Right? We've written equilibrium expressions. This S and this P stand for solubility product, and we'll talk about that in a minute as well. So if you look very quickly, you're used to solubility rules. If not, you can go to a different podcast or to the solubility chart that are on top of the paper on this page right here. And if you look, you've seen things that don't dissolve really well and things that do dissolve. Now, just because this isn't dissolving very well doesn't mean there's some ions that are actually floating around in there. If you actually look, you can see very clearly that this is a dissociation equation, which we'll talk about in a second. And just because something doesn't dissolve very well doesn't mean there's some ions floating around. Now, if I'm not a good dissolver, that means I land on a solubility product constant chart. Yikes. What's that mean? Ksp. Again, solubility product. And so what's solubility product imply? That means that if I wrote an equilibrium expression for these, for instance for AgI, every single one of these compounds, which are, by the way, all ionic compounds, aren't they? Metals and nonmetals, or metals and polyatomic ions. These are all solids, but because they're Ksp values, and I'm looking at them, I know there's a double arrow, right? Equilibrium. And I know that silver ions, and this is called a dissociation equation. I'll talk about that in a second. And iodide ions are floating around. Now, what's true when we write equilibrium expressions? If this was already given to you, you don't include solids. So that means you write silver ions, and they're aqueous, right? I don't need to write AQ. That implies it's aqueous with an ion being there. And iodine ions. And if you notice, this is a K expression, an equilibrium expression, except it's a product, isn't it? That's because there's no reactants here, and so if you actually solve this, wouldn't you multiply these two together? So therefore it's called solubility product. Now, these are all constants because at 25 degrees Celsius, these are always going to dissolve the same in water. Now, what does this mean, this solubility product constant? If you look, there's some different numbers here. For example, this compound has 2.60 times 10 to the minus 5. This is times 10 to the minus 19th. This is times 10 to the minus 29th. The more negative that number and size becomes, then it means that it doesn't dissolve as well. So for instance, something times 10 to the minus 8th is going to dissolve better than something times 10 to the minus 12th, than something times 10 to the minus 23rd. This is a lousy dissolver. They're all lousy dissolvers. They're all not good at dissolving. But this dissolves better, even though it doesn't dissolve very much, which means even though I'm going to have very few ions, I'm going to have some. Even though I'm going to have very few ions, I'm going to have way less than this one. Okay? And I'll talk about that more in the other podcast. But before you do Ksp problems, you need to be able to write dissociation equations. Now, here's that chart again. Okay? If you notice, things like NaCl, sodium chloride, which is an ionic compound, salt water, that's not on this chart. And this is why. Sodium ions and chlorine ions are in solution if I put salt into water. But if you notice, there's no double arrow. And that's because sodium chloride, if I put it in enough water, completely dissolves. It all goes away, and the only thing I have are sodium and chloride ions. There's no need for a Ksp value. That's because all I have are products, which means it's huge. I have no reactants at all. There is no equilibrium. Now, if I look at, for instance, this barium carbonate, what do I have here? I have barium carbonate, I know for a fact that's a solid because it's on a solubility product constant chart, right? That's cut off from the other page, which means it has its Ksp value. I'm going to put a double arrow because it's an equilibrium expression. And I'm going to dissociate it into ions. Barium +2 ions and carbonate ions. Now, what do I have more of? I have way more of this. And I have very little of both of these. And how do I know that? Well, it's on the Ksp chart, and this is my equilibrium constant value. And that K, if you recall, is less than 1, which means I have way more reactants than I do products, which means this is a wussy, really bad dissolver, because I have more of this stuff and very few of these. Okay? Now, if I'm going to solve Ksp problems, which, by the way, equilibrium constant again, right? Products over reactants, I need to learn and remember that there's 3 steps. I need to write the dissociation equation. I need to write directions, or the equilibrium expression. And I need to use molarity from my coefficients. Let's go back through those again. Write the dissociation equation. We'll have practice with that in a second. Write directions, or the equilibrium expression, products over reactants. And use a molarity from the coefficients of my balanced equation. Okay? Now, dissociate. That's my first step. And I'm going to read this problem and say, oh look, it's a Ksp problem, so I know I have to do the DDM, the dissociate, directions, molarity. Now, let's read through this yuckity word problem and see what the heck they're talking about. Well, it says find the Ksp, which tells me I'm doing this kind of problem. It tells me the molar solubility. That's fancy schmancy talk for molarity. Look at this. Isn't this molarity? So I know the molarity of this copper 1 bromide, right, +1 and -1, has a molarity of 2.0 times 10 to the -4th moles per liter. So that means that I'm going to take copper 1 bromide, and I'm going to put it into water. It's a solid right now. And I know I'm going to write a double arrow. How come? Because it's a Ksp problem. I'm going to break it apart into its ions. Copper ion and the bromide ion. And this is a balanced equation. Now, what's my next step? To write my directions. I'm going to write this down here a little bit so you can see. My Ksp, which is products over reactants, remember? Which means I'm going to go ahead and take copper ions and put it in brackets, and bromide ions and put it in brackets. And I don't need to write this aqueous. I'm just writing it here so you can actually see this, okay, for right now. So those copper ions and those bromide ions, that's where they come from here. Okay? So, why don't I include the copper bromide? Because it's a solid. Whoops. I didn't mean to do that. It's a solid. I don't include it in my equilibrium expression, and therefore it's called a solubility product, right? So let me get rid of this aqueous and this aqueous. I shouldn't have put it in there, but I was just doing to show you, okay? Now, what goes in there? I've got my dissociation. I've got my directions. Now I'm going to go ahead and take the molarity from my balanced equation. What did we say the copper bromide was? We said it was 2.0 times 10 to the -4th moles per liter. So let's look at our coefficients. I have 1 here, and for every 1 copper bromide, I make 1 copper ion and 1 bromine ion. So what happened if I had 4 of these? That means I would make 4 of these and 4 of these, yes? So because it's a 1-to-1 to 1 relationship, that means if I have 2.0 times 10 to the -4th moles per liter, molarity, that means I'm going to have 2.0 times 10 to the -4th molarity of this floating around, and 2.0 times 10 to the -4th molarity of this floating around. A 1-to-1 to 1 relationship. Now, we dissociated, we wrote directions. what goes in those brackets? The molarity, correct? So I'm going to go ahead and write 2.0 times 10 to the minus 4th molarity, and that's for my copper ion, and 2.0 times 10 to the minus 4th molarity, and that's for my bromine ion. I'm going to do my math, and when I solve it, I get 4.0 times 10 to the minus 8th, and that is equal to my Ksp. Now, if I'm finding Ksp, that means I have to have a number that's smaller than 1, which means it lands on a solubility product chart, which means it's a really bad dissolver, which means I have a number where K is less than 1. Is that true? Yes, it is. 4.0 times 10 to the minus 8th. Okay, that doesn't dissolve very well. It dissolves better than something times 10 to the minus 24th, but it's still not a good dissolver. Let's try another one. A little more complicated, okay? By the way, this should say moles per liter. And it's at 25 degrees Celsius. I'm putting that in here now because what would happen if I told you a different temperature? If I heat things up or cool things down, don't they dissolve differently? Okay, so it's very important to have that temperature that's in there. So, what are my steps? The DDM. DDM. Dissociate, directions, molarity. So let's dissociate. Well, if I was going to write bismuth sulfide, this is how you write bismuth sulfide, and it's a solid. Why do I know it's a solid? Because I've got a Ksp involved. That means I put a double arrow, and then I write my ions. I've got 2 of these. For 3 of these. And that's my dissociation equation. Now let's stop for a second before we go on, and let's look real quick at our coefficients. This is 1, correct? And for every one of those, I have 2 of these, and I have 3 of these, because I have 2 down here and 3 down here. So that means it breaks apart. For every one of these blobs, I have 2 of these and 3 of these, right? That's the ratio. So let's look at this. Solubility. Remember back here we called it molar solubility. So they can either call it solubility or molar solubility. And what do they really mean? They mean molarity. So what is the molarity? Well, and I'm doing this before we go on, guys, just so you can get this down, because this is a little different. What's my molarity? Well, if this right here is 1.0 times 10 to the minus 15th, and there's 1 of them, isn't this going to be 2 times 1.0 times 10 to the minus 15th? And this is going to be 3 times 1.0 times 10 to the minus 15th. Okay, because it's a 1 to 2 and a 1 to 3 ratio. It was simple back here when it was 1 to 1 to 1, one of these and one of these and one of these. The molarity was just the same. Here, because the molarity is 1 here and twice here, you've got to double it. And once here and 3 times here, you've got to triple it. Okay, so I'm going to erase this, and we'll come back to this. I'll do it one more time when we actually do the problem. All right, now, what do I have here? I dissociated. Now I need to write my directions. What are my directions? My Ksp is a solubility product. I don't include my solid. I do include my bismuth, my ion, and I square it. And I include my sulfide. Oh, I can't believe I did this. I'm so sorry. It's not Si. I'm crazy today because I had to calibrate my pen and it wouldn't work. Sorry. Okay, here we go. Okay, I'll redo this again, but for right now, this works, okay? So, because of the snow. Now, dissociate, directions. My next step is to take my molarity based on my balanced equation. So these are my directions. So I'm going to write my brackets big because I'm going to get ready to write my molarity in there. So if I look in my equation, what do I have for bismuth? I have 2 times whatever my molarity is. What's my molarity? My molarity is 1.0 times 10 to the minus 15th. Okay, so what goes in my brackets here? My molarity for my sulfide ion, not my silicon ion, sorry. Silly me. So what I'm going to do here, what's my molarity? 3 times whatever my molarity is. And then I go ahead and follow my directions. And when I follow my directions and do my math, I get 1.1 times 10 to the minus 73rd. Wow, that's my Ksp value. Look at that. So tell me what kind of dissolver this compound is, bismuth sulfide, compared to the Ksp for copper 1 bromide. Copper 1 bromide doesn't dissolve very well. This dissolves worse. You see that? But the problem is there's still some bismuth and still some sulfide ions floating around. Okay? And if it's dangerous in any way, shape, or form, or if it can react with other things in the environment, then you're in trouble. All right. Third kind of problem. All right. Now, what's this problem? This gives you the Ksp value. And it asks you to find the solubility. What's another way that we can say solubility here? Molar solubility. And what's that really mean? They're trying to trick you. What are they asking you for? The molarity of copper 2 iodate. Okay. So, what are our steps? Dissociate. So let's write copper 2 iodate, which, by the way, that Roman numeral 2, remember, means copper with a positive 2 charge. The iodate ion is this ion, and it's got a negative 1 charge. So if I write my compound, it's CuIO3. I'm going to put my parentheses here and put a 2. Now, I'm going to make this a solid. How come? Because I've got Ksp involved. I'm not finding Ksp. They tell me Ksp, but I haven't involved. That means I have a double arrow. And I write copper, positive 2, aqueous. And there's only one of them, isn't there? Okay. Plus 2 iodate ions. Because there's a 1 to 2 ratio here. Right? That's why there's a 2 out front here and a 1 out front here. Now, let's look at our ratio. For every one of these, what do you have? One of these. For every one of these, how many iodate ions do you make? 2. So that's going to come into play in a little bit. So how have we satisfied our first set of things we need to do? Dissociate. We've satisfied our first requirement. Okay, it's dissociated. What's our second step? Write directions. This is a Ksp problem. So write Ksp equals, and actually I'm going to give us a little more room so you can understand what's going on here again. So I'm going to write Ksp down here. All right, and that equals copper, positive 2, and the iodate ion squared. All right, those are my directions. So I've written my directions, and again, I don't include this because it's a solid. So now that I have my directions, I need to go ahead and put my molarity in. But wait a minute, they don't give me my molarity. They give me a Ksp value. And what's that Ksp value? That's equal to 1.4 times 10 to the minus 7th. Okay, so that is equal to 1.4 times 10 to the minus 7th. I know that that's equal to that. So that means I need to find molarity. Well, if this is 1, and this is 1. If this is 1, then this is 2. So let's call this X. And if that is X, that means this is also X, isn't it? Because it's a 1-to-1 relationship. Now, if this is X, then what's the iodate ion? It's 2X, isn't it? Because whatever X is, this is twice X because of the coefficient in my balanced equation for my moles. Now, what does X stand for? They stand for molarity. So inside my brackets, I'm going to go ahead and copy these because I'm copying my directions down. What goes in those brackets? Don't think about it. Okay, don't think about the craziness of this. This is different, I know. But what goes in those brackets? Molarity. So what is our molarity? We're going to call this x, and we're going to call this 2x. And we know that this is equal to 1.4. I don't mean to rewrite it, but I'm going to so it's clear for you. And there's no units because that's a k value. That's what it's equal to. So we did our dissociation. We wrote our directions, and now we're putting the molarity in, but we don't know the molarity is, so we're going to call it x. So now what do we do? Now we have to solve. So if you look, how do you solve 2x squared? Well, isn't that 4? Because 2 squared is 4 and x squared, right? That's what that is. And this is just x, isn't it? So I have now 1.4 times 10 to the minus 7th. And again, please don't recopy this 1.4 times 10 to the minus 7th over and over again. I'm just doing it so it's clear for you. Equals x times 4x squared, which means that's equal to 4x cubed, isn't it? So how do you solve, right? That's what that turns into. How are you going to solve this? What do you get when you get 1.4 times 10 to the minus 7th equal to 4x cubed? Well, you divide both sides by 4, right? Which means the 4 on this side is going to go away. And to get x by itself, I'm going to go ahead and cube root this whole puppy. That makes me solve for just x, doesn't it? Okay? And that means when I do that, I'm going to come up with a value, put in your calculator, of 3.3 times 10 to the minus third. Now careful, what are we solving? What is x? X is molarity. Okay? So you might want to label your answer first so you don't forget. This is molarity. And that's my molarity of my copper 2 iodate. I warn you because there are units that don't have, values that don't have units, like Ksp, right? It's just a ratio. And units that do, that are molarity. Hopefully this helped you. It's a review of what we did in class. Okay? So take care, and I will see you later.